Welcome to Lecture 2. In this set of lectures, we'll take on the analysis method called simple logistic regression. And hopefully you'll see the results may look different on paper than what we got with simple linear regression because our outcome type is different, but the spirit is exactly the same. So in this set of lectures, we will develop a framework for simple logistic regression, which is a method for relating a binary outcome to a single predictor, and the predictor can be binary as well, categorical or continuous, and the way in which we'll relate these two things, the outcome to the predictor, is again via a linear equation. So in this first section, we're going to take on simple logistic regression when our predictor of interest is either binary, two categories, or more than two categories. So hopefully at the conclusion of this lecture section, you'll understand how logistic regression relates a function of the probability or proportion of individuals with a binary outcome to a predictor via a linear equation. And you'll be able to interpret the resulting intercept and slope or slopes from a simple logistic regression model when the models either include a binary or categorical predictor. And in the next section, we'll take on the situation where the predictor is continuous. The first thing we have to establish formally is what the left-hand side of the linear equation for logistic regression looks like. And this is a bit more convoluted than it was with linear regression. With linear regression, the left-hand side was simply the estimated mean of the continuous outcome, and we were predicting that via a linear function of our x1. For logistic regression, we have to work off a function of the probability or proportion of having the binary outcome. If the binary outcome is a y coded as 1 if the outcome occurs and 0 if not, then we're looking at the proportion or probability that y equals 1. And the function we're going to use, we're going to start by looking at the odds of the outcome occurring. And recall odds is just the probability of it occurring divided by the probability of it not occurring, but we're going to look at this on the log scale. So our equation is going to relate the log odds of a binary outcome to a single predictor x via this linear equation. And as noted previously, for any type of simple regression, x can be binary, nominal categorical, ordinal categorical, or continuous. As with everything else we have done thus far, we're only going to be able to estimate the regression equation from a sample of data. So to indicate the estimates that the slope and intercept, we get our estimates, again, just like we did before, we'll put hats on top of them. Technically speaking, we're only going to be able to estimate the relationship between the sample-based log odds and the predictor via this equation. So we should put hats on these p's here to indicate that we're estimating the proportions that in turn are used to estimate the odds and the log odds based only on our sample. But that is not consistently done in the literature. The hats are left off of the p's, so I will, from here on in, not include them. And you might say, well, log odds, that doesn't sound like a very natural way of thinking about things. And for the moment, just take it on faith, if you will, if you trust me. But in the next section, when we delve in the situation where x is a continuous predictor, we'll explore the reason for this choice of scaling and see why it's necessary and appropriate. So what we've got here ultimately will be an equation where if you give me the value of x1 for a group of persons or subjects, I can plug that into my equation and estimate their log odds. And this slope of x, remember when we started talking about linear equations, we focused on the comparisons being made by the slopes. And we said generically a slope compares two groups' estimate of the left-hand side for two groups whose x value differs by 1. So what the slope does here is it compares the log odds of the binary outcome for two groups who differ by 1 unit of x1. And hence this slope estimate is interpretable as an estimated difference in the log odds of the outcome between two groups who differ by 1 x value. You might say, well, that's not very helpful. What is the difference in log odds? How can I make sense of that? Well, you may recall those wonderful property of logarithms, and one of them includes the fact that the difference in logs can be re-expressed mathematically as the log of a ratio. So generically speaking, I'm going to write out what the slope estimates here. It estimates the difference in the log odds of the outcome for a group whose x1 value is, I'm just going to call it a plus 1. The value of x1 is a plus 1 minus the log odds for a group whose x1 value is 1 unit less. I'm just trying to be generic here and not put in specific numbers. For the group whose x1 value is a. A could be any number. The point is that the two groups being compared here in this difference differ by 1 unit in the predictor. So you may recall that the difference in the log of one thing minus the log of another can be re-expressed as the ratio of the first thing that we're taking the log of, the odds for the group whose x1 value is a plus 1, divided by the odds, or the second thing we're taking the log of, the odds for the group whose x value is a. And the log of the difference can be re-expressed as the log of the ratio of those two things. So now we're starting to see something that looks a little familiar. Odds divided by odds is nothing more than an odds ratio. The odds ratio comparing the odds of the outcome for two groups who differ by 1 unit in x1. And so what this slope is the log of an odds ratio. And we'll see with a concrete example in numbers in a minute, if we have the log of an odds ratio, we can exponentiate or anti-log that to get an odds ratio estimate. So let's start with an example. Let's go back to our data on anthropometric measures and other measures from a random sample of Nepalese children, but I'm going to expand the age range here to be between 0 and 3 years. So we can explore the relationship between breastfeeding and characteristics of children up to 3 years old. So the first thing we're going to look at is we're going to see if there's any relationship between breastfeeding and sex of the child, and we're going to quantify that. And so in our data set, the proportion of children in this age group who are breastfed is 3/4 or 75%, and the sex distribution slightly favors females in the sample. 52% of the sample is female, the remaining 48% is male. Now we've seen several times now, if we want to handle a binary predictor such as sex as an X, we can make one of the groups coded a 1 and make the other group coded 0, the reference group. And so just to mix things up, I'm going to make males the 1s and females the 0 or reference group for this analysis. So what we're going to end up doing is estimating a logistic regression that looks like this. The log odds of being breastfed, and I'm just going to shorten that to log odds, equals an intercept plus a slope times our value of sex, x1. And despite the fact that this is an equation, we're really only estimating two outcomes here. The log odds of being breastfed amongst the males and the log odds of being breastfed amongst the females. So let's just to get a little more practice in understanding what the difference in log odds is, let's write out the estimated log odds of being breastfed for both these sex groups. So if we do males, this is the log odds when x1 equals 1. We put our intercept, beta naught hat, plus our slope times 1. And so the log odds estimate for male children is the sum of the intercept and that slope, beta 1 hat. For female children, their value of sex is 0, so when we plug that in, this part disappears, is just the intercept. So again, beta 1 here is the difference in the log odds being breastfed for males minus the log odds for females. Another way to think about this is what we said before. It's the difference in the log odds being breastfed for males minus the log odds of being breastfed for females. And we've seen before, we just saw that this could be re-expressed as the log of the ratio of the odds being breastfed for male children relative to the odds of being breastfed for female. So this slope has a log odds ratio interpretation. What about the intercept? Well, we saw that when we looked at the log odds for the reference group, the log odds for the females, whose value of x1 is equal to 0, we got the intercept. So this intercept estimates the log odds of breastfeeding for one group. The estimated log odds of breastfeeding for females. And we could certainly translate that into an odds, and we'll show in a subsequent section how to backtrack or back compute this into an estimated probability of being breastfed for females, for example. So here's the resulting equation we get if we use a computer. We get the estimated log odds of being breastfed is equal to an intercept of 1.12 plus a slope of 0.002 times sex. So this slope of 0.002 again estimates the log odds ratio of being breastfed for males compared to the reference group of females. And the intercept is equal to the log odds of being breastfed for female children in the sample. So these things are not so informative or helpful on the log scale. So let's take things and anti-log them to get some clarity. So this beta 1 estimate is 0.002. That's the estimated log odds ratio of breastfeeding for males to females. So if we exponentiate this, this will give us the estimated odds ratio. E to the 0.002, which is about equal to 1.002. So what does this suggest? The odds ratio of being breastfed for male children to female children is 1.002. Essentially, there's no difference in the odds. There's a slight 0.2% higher odds that males are breastfed relative to females, but this ratio is very close to 1. What does the intercept estimate? Well, the intercept here is equal to 1.12. This is the log odds. This does not compare two groups. It's the log odds of being breastfed for one group, the reference group, the group with x1 equals 0, females. If we exponentiate this, take e to the 1.12, you get 3.06. This is the estimated odds that females are breastfed. So they're roughly 3 to 1 that females in this sample are breastfed. And very shortly, and you may even be able to do it now if you think about it, but we'll show how to convert an odds estimate for any one group to a probability or proportion that that group has the outcome. So we'll be able to translate that into the estimate of the probability of females in the sample being breastfed. You know, the coding choice again for this binary predictor is completely arbitrary. For this breastfeeding and sex analysis, I wanted you to think about what the values of the intercept and slope would be if sex was coded as a 1 for females and a 0 for males, and then what would the subsequent odds ratio comparing males and females and the odds for females look like under this scenario. And I'll leave this to the review exercises. So you can start thinking about now, but actually go through it if you choose to when you do the review exercises. Let's look at another example. This was a study published in 2010 in the Journal of the American Medical Association looking at the risk of respiratory failure after birth and gestational age. So what they did was they looked at their context here was they were considering late preterm births. They account for an increasing proportion of prematurity associated short-term morbidities, particularly respiratory, that require specialized care and prolonged neonatal hospital stays. And they wanted to assess short-term respiratory morbidity in late preterm births compared with term births in a contemporary cohort of deliveries in the U.S. And so they used retrospective electric data records from 19 hospitals across the U.S. And they gathered an impressive amount of data on over 230,000 deliveries in these 19 hospitals between 2002 and 2008. And what they used ultimately was a multiple, which we'll get to shortly, logistic regression analysis comparing the risk of respiratory failure by gestational age. So we're going to look at an unadjusted analysis to get this started. So here's the from their data set collected from U.S. records, the majority, or 90% of the sample, had full-term gestational age is 37 to 40 weeks. Another 5% came in at a late preterm at 36 weeks, another 3% at 35 weeks, and the remaining 2% had a 34-week gestational age. So even though the gestational age categories are ordinal, the authors did not want to assume, and we'll talk more about this in the next section, but if we were to treat this as a single measure and use the ordinality, we would assume that the log odds linearly increases or decreases the log odds of respiratory failure with increasing gestational age, and maybe the jump isn't consistent for each additional week of gestational age. So what we're going to do just to explore this is treat this as categorical to start, and we'll talk a little bit about the ramifications of that, but I'm going to make 4 categories, okay? And what we're going to do is make 1 the reference, and we're going to use the 4 categories I laid out before, 34, 35, and 36 weeks, and then 37 to 40 weeks. So we've got 4 categories, and so what we're going to do is, like we've done with categorical variables in linear regression, we're going to make 1 group the reference and then create binary indicators separately for each of the 3 other groups. So I'm going to be consistent with how the authors did it. We're going to use full-term births, 37 to 40 weeks, as the reference, and then we're going to create individual indicators for births that were at 34 weeks, 35 weeks, and 36 weeks. And we're going to estimate a logistic regression equation that looks like this. We're going to rate the log odds of respiratory failure to these indicators via this equation. So what do we get? For example, if we're in the, so let's think about this. Suppose we're looking at children who were born at 34 weeks. So x1 equals 1, x2 equals 0, x3 equals 0. Well, this equation is going to estimate the log odds of respiratory failure for this group to be the intercept plus beta 1 hat times 1 plus the other slopes times 0. So the estimated log odds for the group born at 34 weeks is beta naught plus beta 1 hat. For the reference group of 37 to 40 weeks, all x's are zeros. And the log odds for this group at 37 to 40 weeks is simply the intercept. So this slope for the indicator of 34 weeks is going to estimate the difference in the log odds of respiratory failure for those born at 34 weeks compared to the reference of 37 to 40 weeks. So you can go through and show, we've shown via that setup that the intercept is interpretable as the log odds of respiratory failure for the reference group. We showed that the slope beta 1 is equal to the difference in log odds of respiratory failure for the gestational age group of 34 compared to the reference. And a difference in log odds, as we've shown, is interpretable as a log odds ratio. You can go ahead and prove to yourself that beta 2 hat estimates the log of the odds ratio of respiratory failure for the group x2 equals 1, which is the group with 35 weeks gestational age compared to the same reference as we had before, and that beta 3 hat is the log odds for the group with 36 weeks of gestational age compared to the reference of full-term births. So here's what the results look like. The estimated intercept is negative 5.5. The slope for x1, the indicator of gestational age, 34 weeks is 3.4. The slope of x2, the indicator of gestational age being 35 weeks, is 2.8. And the slope of x3 is equal to 2.0. So let's just think about this for a minute. So this is 2.0 is the difference on the log scale between the group with 36 weeks of gestational age compared to the reference of 37 to 40. So the difference for that 1 unit difference, if you will, I've lumped 37 to 40 together, but you can think of them as qualitatively 1 unit higher than 36 weeks, is 2.0 on this scale. The difference between the group at 35 weeks and that same reference is 2.8. So this difference doesn't double when we go up by 1 unit in gestational age. It compounds by another additional 0.8, but it doesn't double. And then when we go to 34 weeks compared to the reference, we get another 0.6 because the difference between this group and the reference is 3.4. So it doesn't appear that the association or the difference between these resulting lower gestational ages and the reference is strictly linear, that this difference does not compound constantly for each 1 unit increase in gestational age. And as such, it's a good idea then that we made these categorical as opposed to treating it as continuous, because incrementally the additional increase in odds is not the same for a 1 unit increase in gestational age across these 3 levels, these 4 levels. So let's try and make sense of this. So let's start with some odds ratios. So we said beta 1 hat equals 3.4. So e to the beta 1 hat equals the odds ratio of respiratory failure for kids born at 34 weeks compared to the reference of full term. That's equal to essentially 30. That's pretty shocking. This suggests that the relative odds of respiratory failure are 30 times that of the reference group for the group that was at 34 weeks. So just a huge increased risk because the odds is increased by 30 times here. We do the comparison for the 35-week gestational age group to the same reference. That's 2.8. If we exponentiate that, that's beta 2 hat, e to the 2.8 is 16.4. So not as high an increase as with the 34-week holds at gestational age of the 34-week group, but certainly a substantial increase in the odds of respiratory failure. And then if we do the last group and exponentiate that 2.0, it's 7.4. So I think certainly getting closer to term is better, but being preterm, regardless of whether it's 34, 35, or 36 weeks, is associated with a large increase in the relative odds of having respiratory failure. What is that intercept interpretable as? Well, it's the log odds of respiratory failure for the reference group, the full term group. And that's equal to negative 5.5. We exponentiate this to get the odds for this group. This is at least some good news here. The odds is 0.004, which is relatively low, and we'll see translates into a low probability. So luckily the probability of respiratory failure, and I haven't shown it explicitly, is low in the group with the best outcomes. And it's certainly worse for the other lower gestational ages, but hopefully, and we'll talk about this in a subsequent section, hopefully this doesn't result in a large probability of respiratory failure, even though the odds are increased by a sizable amount. So in summary, logistic regression, again, is a method for relating a binary outcome to a predictor, x, via a linear equation. And the predictor can be binary, categorical, or continuous, but we've only considered the first 2 situations thus far. What we get is a linear equation that relates the log odds of the binary outcome to the predictor of interest. And we've shown that the slopes from the logistic regression for our x or x's have log odds ratio interpretation and can be exponentiated to estimate odds ratios. And the intercept for these situations estimates the log odds of the binary outcome for the groups whose x or x values are 0. So in the next section we'll continue working on these ideas, but we'll talk about the situation where we treat x as a continuous measure.